So we begin the next part of this course, or we could call it module 3 or chapter 3 if you will, Fejer's theorem and its applications. So what is Fejer's theorem? Remember that I talked about the various modes of convergence: pointwise convergence, mean convergence and Cesaro convergence. We already discussed pointwise and mean convergence. Now we take the third different type of convergence called Cesaro convergence or Cesaro summability of the partial sums of a Fourier series. So now let us recall a very simple result in real analysis. You have probably seen this in your undergraduate courses, but nevertheless let us quickly recapitulate this result. This result is called the Cauchy's first limit theorem. What does Cauchy's first limit theorem say? Let us look at theorem 22 on the slide. Suppose Bn is a sequence of real or complex numbers converging to L, then the sequence of arithmetic means 1 upon n times b1 plus b2 plus etc. plus bn. The sequence of arithmetic means converges to L again. Intuitively this is very clear. You see, let us think about the following situation. Suppose for example you have a class with say 60 students and you are looking at the average scores in the mathematics examination, and suppose the average happens to be say 60. Now there may be students scoring 93 and there may be students scoring 0, and somehow the average has come to 60. Now let us do a thought experiment. Let us enlarge the class. So the 61st student, the 62nd student, and as we add larger and larger number of students, assume that their marks are close to 60. And so what will happen when I take averages over larger and larger population? So now I am adding 1000 more students to your class, but the additional students have marks hovering around 60, 61, 59, 59 and a half, 61.3, etc. So now I take the averages of the first 60 and the first 100, the first 1000, larger and larger subpopulations. Then what will happen to 1 upon n b1 plus b2 plus bn? When n goes from 60, n goes from 70, n goes 80, 100, etc. These averages will come closer and closer to 60. Now let us look at this situation. You got a sequence bn converging to L. That means beyond a certain stage, these numbers bn are close to L. So now if I start taking the averages over larger and larger strings, so the average of the first n numbers where n becomes larger and larger, then these arithmetic means will come closer and closer to L. That's exactly what the theorem is trying to say. Intuitively, it should be obvious. So let's get to the proof of this theorem. The proof is very simple. It's as simple as the intuition itself. In fact, it is just this intuition converted into a proof. So let us first begin with some preliminary algebra. The arithmetic mean 1 upon n b1 plus b2 plus etc. plus bn minus L in absolute value. What is that going to be equal to? Do the algebra. It is 1 upon n times absolute b1 minus L, b2 minus L, etc. bn minus L. That's pretty easy. The last displayed equation in your slide. So now let us apply the triangle inequality and split the right hand side into two pieces. Namely, I take the first n1 terms and the last n minus n1 terms, and I group them into two pieces. Now this is true for any n1. What is going to be my n1? I shall presently specify. I shall presently specify what the n1 is going to be, but this inequality that you see displayed in the slide is true for any n bigger than n1. Now before we specify the n1, let us make an observation that a convergent sequence is obviously bounded. So the bn's converge, and so bj minus L must be bounded. There must be a m positive such that mod bj minus L must be less than or equal to m for all j. Hence, Look at the first piece, 1 upon n times mod b1 minus L plus etc. plus mod bn1 minus L. Together all these things are less than n1 m upon n. b1 minus L, b2 minus L, absolute value, they are all less than or equal to m. So, you get n1 m upon n. The second piece, 1 upon n into mod bn plus 1 minus L plus etc. plus mod bn minus L. Now, we bring in the epsilons. Let epsilon greater than 0 be arbitrary. There is an n1 such that mod bn minus L less than epsilon by 2 for all n bigger than or equal to n1. Because the bn converges to L, I simply applied the epsilon definition of convergence. So, now let us see where we are now. 1 by n, b1 plus b2 plus etc. plus bn minus L in absolute value is less than or equal to n1 m upon little n plus n minus n1 upon n epsilon by 2. Now, n minus n1 upon n is a fraction, it is a proper fraction. So, that is less than 1. So, we get n1 m upon n plus epsilon by 2 if n is bigger than n1. So far is very clear. Now, we need to select the n in such a way that the first piece n1 m upon n is also less than epsilon by 2. So, if we select our n naught such that first of all this new n naught must be bigger than the old n1, so that we have gone past n1. So, whatever we have done earlier continues to hold. Now, we select our n naught in such a way that n naught is bigger than 2 n1 m upon epsilon. If that happens, then when n is bigger than n naught, then n will be bigger than 2 n1 m upon epsilon. So, the piece n1 m upon n will be less than epsilon by 2, and we will get the result, namely that the arithmetic means 1 upon n b1 plus b2 plus etc. plus bn minus L in absolute value is less than epsilon when n is larger than n naught. And this completes the proof of the Cauchy's first limit theorem. The converse is obviously false. Why? Take the sequence 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. This sequence does not converge. But if I take the sequence of arithmetic means, it does converge. So, the original sequence may not converge, but the sequence of arithmetic means converge. So, the converse is not true. So, the point is, if the original sequence converges to L, the sequence of arithmetic means also converges to L. So, now the question is, the original sequence may not converge, but the sequence of arithmetic means may still make sense. So, now let us say that a sequence converges in a generalized sense if the sequence of arithmetic means converges to L. So, this generalized notion of L agrees with my conventional notion when the original sequence converges. So, we are enlarged or we are generalized the notion of convergence. This generalized notion is called Cesaro convergence. You say that a sequence Bn converges in the sense of Cesaro if the arithmetic means 1 by n of b1 plus b2 plus etc. plus bn converges. So, now let us take the next one. The definition is formally there. A sequence is said to converge in the sense of Cesaro, the arithmetic means converge to L. In particular, Cesaro convergence implies convergence, as we have seen above. Now, coming back to Fourier series, we have seen that if a continuous function, if we have a 2 pi periodic continuous function, its Fourier series may not converge. The partial sums may actually diverge. In fact, it may diverge in a large number of points. We already discussed this in module 1 in the chapter on pointwise convergence. The theorem of Fejer asserts that if we have a 2 pi periodic continuous function, then the partial sums of the Fourier series will always converge in the sense of Cesaro. That is, the Sn fx will Cesaro converge to f of x. In other words, the arithmetic means of the sequence of partial sums will converge to f of x. more is true, the convergence will actually be uniform, and this uniform convergence is going to be quite significant, which is what makes Feyer's theorem very useful. I mentioned uniform convergence. Let us quickly recall what uniform convergence means. A sequence of functions f and x, all defined on a common domain E, is said to converge uniformly to f of x if supremum mod fn x minus fx goes to 0 as n goes to infinity, where the supremum is taken over E. We already used uniform convergence in the proof of Riemann-Lebesgue lemma. Remember, we proved the Riemann-Lebesgue lemma for polynomials, and we used Weierstrass approximation theorem, which says that if you take any continuous function, there is a sequence of polynomials converging uniformly to it. We use this fact to prove the Riemann-Lebesgue lemma. So, uniform convergence has already been used before. Here are some exercises on Cesaro convergence. Suppose Bn is a monotone increasing sequence of real numbers, then the arithmetic means will also be monotone increasing. If Bn is a monotone decreasing sequence of real numbers, then the sequence of arithmetic means will also be monotone decreasing. So, monotonicity is going to be preserved by taking averages. Now, suppose I take a sequence Bn of positive real numbers. This time I want the numbers to be positive real numbers, and I take the geometric mean of these numbers. What is the geometric mean? Take the product of the first n numbers b1, b2, bn, and take the nth root. Call it gn. Gn is called the geometric mean of b1, b2, bn. Then the geometric mean will also converge to L if bn converges to L. The Cauchy's first limit theorem says that if Bn converges to L, the arithmetic means converge to L. Now we can also prove that if Bn converges to L and Bn is a sequence of positive real numbers, then the geometric mean also converges to L. What is the harmonic mean? If you take n numbers B1, B2, Bn, you take the reciprocals, and you take the arithmetic mean of the reciprocals. The arithmetic mean of the reciprocals will have dimension inverse of the dimension of the original sequence. Suppose you are taking the average of, say, heights of students. Now, if I take reciprocals of these numbers, what is the dimension? 1 upon meter to the power minus 1. And so the average will also have dimension meter to the power minus 1. So, I must take the reciprocal again, so that the final number has the same dimension, namely that of height. So, what is the harmonic mean? The harmonic mean is the reciprocal of the arithmetic mean of the reciprocals. So, take the numbers, take the reciprocals, take the arithmetic mean of the reciprocals, and take the reciprocal again, namely Hn equals n into b1 to the power minus 1 plus b2 to the power minus 1 plus etc. plus bn to the power minus 1, the whole raised to the power minus 1, as you see displayed in the slide. This is called the harmonic mean. Of course, in order for this harmonic means to make sense, the numbers must be non-zero. So, let us assume the numbers are all strictly positive. So, what does the theorem says? The theorem says that if you have a sequence of positive real numbers which converges to L and L is also positive, then the harmonic means Hns also converges to L. Prove this fact. In fact, this will immediately follow from the Cauchy's first limit theorem, because Bn converges to L. So, Bn inverse will converge to L inverse. So, the arithmetic means of Bn inverse will also converge to L inverse. So, the harmonic mean will also converge to L. This last part immediately follows from Cauchy's first limit theorem. So, now you deduce from this that if Bn is a sequence of positive real numbers such that Bn plus 1 by Bn converges to L, then the nth root of Bn also converges to L. You may recall when you study infinite series that when you have an infinite series, you first want to apply the ratio test. You try to apply the ratio test and you find that Bn plus 1 by Bn converges to 1. The ratio test has failed. Then you apply the root test. Again you find that the nth root of Bn has limit 1 and the root test again failed. Why does this happen? This happens because of this phenomenon, that is, if Bn plus 1 by Bn converges to L, then the nth root of Bn also converges to L. This important result is called the Cauchy's second limit theorem. As a particular case, you prove that if you take the nth root of n factorial upon n, it converges to 1 upon e. Namely, n factorial to the power 1 upon n divided by n converges to 1 upon e. The last exercise that you see can be thought of as a very weak form of the celebrated Stirling's approximation formula. What does it say? N factorial to the power 1 upon n is approximately n upon e, because n factorial to the power 1 upon n goes to 1 upon e. So, n factorial to the power 1 upon n approximately is n upon e. It is very tempting to raise it to the nth power and say that n factorial is approximately n to the power n into e to the power minus n, but that is not true. We may have missed a multiplicative factor, and indeed we have missed out an important multiplicative factor, and that important multiplicative factor is root 2 pi n. So, the precise version of the Stirling's approximation formula is n factorial is approximately equal to n to the power n into e to the power minus n into square root of 2 pi n, when n is very large. That is theorem 25 that you see on the slide. The Stirling's approximation formula is a very old formula, goes back to James Stirling in his Methodus Differentialis, which appeared in 1730. It is almost 300 years old, and its importance was quickly recognized by the mathematical community. Laplace used it in his monumental work on analytic theory of probability, when he derived what should be the precursor of the central limit theorem. It is called the de Moivre-Laplace's theorem. The Stirling's approximation formula plays a very crucial role there. It was generalized to gamma functions. Gamma n plus 1 is n factorial. So, the gamma function is a generalization of the factorial. So, gamma x plus 1 is approximately x to the power x into e to the power minus x into square root of 2 pi x when x is very large, positive. Now, let us come back to Fejer's theorem. What does Fejer's theorem say? Suppose f of x is a 2 pi periodic continuous function on the real line and Sn fx is the nth partial sum of the Fourier series of f of x, then limit as n tends to infinity 1 upon n into S naught of f of x plus S1 of f of x plus etc. plus Sn of f of x equal to f of x uniformly. The arithmetic means that you see, equation 3.1, you see the partial sums Sn fx and you look at its arithmetic means. The arithmetic means give you the function f of x. Okay. We begin by the formula for the jth partial sum of the Fourier series. Remember, what is the jth partial sum? We got a expression, an integral expression for the jth partial sum, right, in the first module. The Sj fx is integral minus pi to pi dj of x minus t f of t dt, where what is my dj? dj is the Dirichlet kernel. dj theta is 1 upon 2 pi sine j theta plus theta by 2 divided by sine theta by 2. We derived this expression in module 1. So, that is your Sg of f of x. Now, what must we do? We must put j equal to 0, 1, 2, 3 up to n and add up. So let's add up and see what happens. So S naught of f of x plus etc. plus Sn of f of x is what? Integral minus pi to pi. All of them have an ft in common, and so it will simply be d0 of x minus t plus d1 of x minus t plus d2 of x minus t, etc. So let us call this kn tilde of x minus t. So what is kn tilde? Kn tilde of theta equal to 1 upon 2 pi times sine theta by 2 into sine theta by 2 plus sine 3 theta by 2 plus etc. plus sine 2n plus 1 theta by 2. Use the expression for the Dirichlet kernel, sine j theta plus theta by 2 divided by sine theta by 2. The sine theta by 2 is common in all the terms. So now let us multiply the numerator and denominator by 2 sine theta by 2. What do we get? Kn tilde equal to 1 upon 4 pi sine squared theta by 2 into big bracket. What do we get? 2 sine squared theta by 2 plus 2 sine theta by 2 sine 3 theta by 2 plus etc. plus 2 sine theta by 2 sine 2n plus 1 theta by 2. What should we do at this stage? We must recall the defactorization theorem, right? 2 sin A sin B equals cos of A minus B minus cos of A plus B. So let us use that formula over here. 2 sin squared theta by 2 is of course 1 minus cos theta. 2 sin theta by 2 sin 3 theta by 2. That will be cos theta minus cos 2 theta, etc. You get a telescoping series, lot of cancellations takes place, and we are simply left with 1 minus cos of n plus 1 theta, and the denominator is 4 pi sine squared theta by 2. Now I must write 1 minus cos n plus 1 theta as 2 sine squared n plus 1 by 2 theta. That's what I am going to do next. Also, one more thing we must not forget. Remember, we are taking the averages. So what have we done? We have added S naught of fx plus S1 of fx plus etc. Sn of fx. How many terms have we added? N plus 1 terms. So when you take the averages, we should divide by n plus 1. So let us divide by n plus 1, and so we should be looking at kn tilde divided by n plus 1. Let us simply call it kn theta. So kn theta is now 1 minus cos n plus 1 theta upon 4 times n plus 1 pi sine squared theta by 2. As I said, the numerator can be written as 2 sine squared n plus 1 theta by 2. 1, 2 cancels out, and we get the expression 3.3 displayed in the slide. This expression is called the Fejer kernel. Now this Fejer kernel is extremely nice because the numerator is positive and the denominator is positive. Unlike the Dirichlet kernel is positive and negative. The Dirichlet kernel oscillates frequently. The Fejer kernel does not oscillate. It's always positive. It is this positivity of this Fejer kernel that makes it extremely useful, and it is this positivity which really does the trick of uniform convergence. Now let us look at some of the properties of the Fejer kernel. What are the properties of the Dirichlet kernel? When I integrate dj from minus pi to pi, I get 1. But how do I get the Fejer kernel from the Dirichlet kernel? I simply do the averages. d0 plus d1 plus da 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 plus dn upon n plus 1. And now if I integrate it from minus pi to pi, again I am going to get 1, right? Because every one of the terms integrates to 1 from minus pi to pi. So when the averages will integrate to 1. So because integral minus pi to pi dj theta d theta is 1 for each j, integral minus pi to pi kn theta d theta equal to 1, equation 3.4 in the slide. What should we do now? Multiply by f of x. So, we get integral minus pi to pi fx kn theta d theta equal to fx. So, that is the next thing that we do. So, first of all, let us recall what have we derived, 1 upon n into s naught of fx plus s1 of fx plus etc. plus Sn of f of x, that is equal to integral minus pi to pi kn of x minus t ft dt, which is the same as integral minus pi to pi knt of f of x minus t dt. That is easy. And f of x equal to integral minus pi to pi knt f of x dt. Now, we must subtract. When we subtract, what do we get? The difference 1 upon n times s naught plus s1 plus etc. plus Sn, the average minus fx. Let us call this difference delta nx. Take the absolute value also. So, what do we get? Delta nx, the absolute value, less than or equal to integral minus pi to pi knt into absolute value of f of x minus t minus f of x dt. The last displayed inequality in this slide. What is our objective? Our objective is to show that delta n goes to 0 uniformly. The arithmetic means converge to f uniformly. That is the statement of Fejer's theorem. So, we must show that delta nx must go to 0 uniformly with respect to x as n goes to infinity. We must understand what happens to the integral. In other words, we have to show that integral minus pi to pi knt into absolute value of f of x minus t minus f of x dt goes to 0 uniformly. We shall take that up next.